All right, here we go. Lesson 11.8. Here's your homework. All right, so today's lesson is on geometric probability. Combine two things that you didn't think could ever be combined, geometry and probability. No pun intended, but you probably haven't done probability since 8th or 9th grade. All right, remember what the processes of calculating probabilities of a game? Well, let's review that real quickly. Some definitions first. So play a game, right? Any game you want. So I'm rolling two dice, right? That's the game itself. And it looks like I got a 1 on one dice and a 1 on the other one. So I got a roll of 1 and 1. 1 plus 1 is 2. So we would say I got a 2 on this roll. What we just did there is an event. That is one of many possible outcomes that occur during a game. So that rolling of a 1 and a 1 is called an event. That's our first definition. The second definition is, well, think about everything that could happen when you play that specific game. Now, the game is rolling two dice. One of the events would be rolling a 2, but if we think about it, well, I could roll a 3, I could roll a 12, I could roll a 10. Sometimes there's more than one way of rolling something. For instance, rolling a 4, I could roll a 1 and a 3 or a 2 and a 2. If I combine every single possible event that could occur when I play this game, all of those together are called outcomes. So outcomes are all the events that could occur during a game of chance. Now, we're calling this a game of chance. Probability is used for many different things. So even though we will call it a game, it may not be a literal game. For instance, you may hear, what's the probability that it rains this afternoon? Well, we don't think of that as a game of whether it rains or not, but we would still say the event is it rains, and all the outcomes would be, does it rain or does it not rain? All right, just so you know, this branch of mathematics is called gaming theory. And then gaming theory includes lots of things, to include the field of probability. All right, so if we think about the game of rolling two dice, these are all the things that could happen. The first dice could be a 1, and the second dice could be a 1, 2, 3, 4, 5, 6. First dice could be a 2, and then we get a 1, 2, 3, 4. So you can see where I'm going. If you have a space or an area that shows all the possible outcomes, that's called a sample space. You don't need to write that down. But let's see, how many possible things could occur during this game? Looks like there's 6 in each row. 6 times 6 is 36. There's 36 possible outcomes of this one particular game, rolling 2 6-sided die. Now, on to what we're doing today. Today, we're doing probability. And I don't know if you remember the definition from the last time you had a class on probability, but probability is the chance of an event occurring compared to how many or how, this is how things could occur. So, compared to how many things could occur. This should be the words, how many things could occur. Well, it's going to be a ratio, and it's the ratio of, well, how many ways could that one specific event occur? For instance, rolling a 2 using 2 die, well, there's only one way. I have to roll 1 on both pair of die. But if I were to roll a 4, well, there's a couple different ways. I can roll a 1 and a 3 and a 1, or a 2 and a 2. So there's 3 different ways. But all the things that could occur when you roll 2 dice, there's 36 of them. So if the game was rolling 2 dice and the event was rolling a 2, there's only one way out of 36, and that's its probability. Now, more formally, we're going to define probability as a number between 0 and 1. And so if I divide 1 by 36, we get to a decimal that's between 0 and 1. I don't know if you remember this, but if you get a probability of 0, that means the event cannot occur. And if you get a probability of 1, that means the event must occur. Now, 1 over 36 is okay, even 0.03 is okay, but usually we want to state probability as a percent. So it's pretty easy to change that to a percent, 3%. So there's a 3% chance when you roll 2 die that you will get a 1 and a 1. In other words, you roll a 2. So that's pretty low probability. So likelihood of getting a 2 is very low. All right, how about we just restrict so we can make the math a little bit easier. How about we restrict ourselves to one die? So I'm going to roll one die and let's think about the probability. So what's the probability of rolling a 4? So I'm only rolling one die this time. So let's think, how many different ways are there to get a 4 if I'm only rolling one die? Well, there's only one way, and there's 6 possible things that can occur: a 1, 2, 3, 4, 5, or 6. So 1 over 6, change that to a decimal, change that to a percent, and now we have a 17% chance. Well, that's a little bit higher than 3%. It's still pretty low. So the chance of getting a 4, just rolling one die, is still relatively low. I mean, high, I guess we would define as over 50%, right? What's the probability of getting an even number? Okay, we'll see. How many even numbers are there on a 6-sided die? 2, 4, 6, there's 3 of them. So 3 out of 6 are 50%. All right, so you have an even probability. Likelihood, is 50%. And it doesn't mean that every other time you're going to get an even number. You can get, 26 odd numbers in a row. The die doesn't care what the previous roll was. It's independent of any one specific roll. But if we were to do this, let's say 1 trillion times, then roughly half of the times we get an even number, and the half the times we get an odd number. This isn't a formal class on probability, but I will bring up some things about probability as the talk continues. Lastly, what's the probability of rolling a 4 or a 1? So that means you win if you roll a 4 or a 1. Well, it's only one die, so there's still only one way to get a 4, but there's also one way to get a 1, so that's 2 ways to win out of 6, so that's a third, so 33%. All right, so hopefully that stimulates some past memories of calculating probability. Today we are going to calculate probability. However, the but here is that it's going to be about geometric probability. And geometric probability, you're probably questioning what that would be. Well, you got to have a piece of geometry. So here's one, there's a segment. Well, in fact, I got 3 segments there. I've got AB, AC, and CB. And it looks like the length of AC is 5 and the length of CB is 3. So what in the world would they be asking? So here's a typical geometric probability question. It says, if a point on AB is picked at random, that means you must touch a point somewhere between A and B. It could be A, it could be B, but it's got to be somewhere between A and B. What's the probability the point that you choose is somewhere on AC? Well, let's think this through. It's kind of like the previous one. Well, how many ways are there to win? Well, what defines winning? Winning means you land on AC, and we don't say there's 5 ways, but the distance between A and C is 5, and the distance between C and B is 3. So the total distance, that would be, you're going to land somewhere between A and B. Well, that total distance would be 8. So we would say that the number of ways that this could occur, landing somewhere on AC, there's 5 units there. So 5, or the length of AC, over the length of the entire thing. And the entire thing is 8. So 5 over 8. And once again, we would much rather have this as a percent. So it looks to be 62.5%. So the likelihood of choosing a point of random on AB and for that point to be somewhere between A and C is likely, right? It's 62.5, 63%. Does that make sense? All right, let's do another one. So here's your typical one. You have some sort of region defined, and the larger region, the light, I believe that's green, the light green one there is region S, and the smaller region, the blue one there, is region R. And so this is one of those ones where they say, a point on region S is picked at random. What's the probability that you chose somewhere in R? And you're like, well, how do I do this? There's no numbers. Do you want me to calculate the area? I don't recognize any of the shapes. And they're not asking you to, well, I guess they are literally asking you to calculate the areas of those 2 shapes. But clearly we can't because there's no numbers involved. But we can use some words to describe this. Well, it's still the same probability. Well, what defines winning? That means you land in R. So let's see, the area of sector R divided by the area of sector S would be that probability. Not a very satisfying answer. You want an actual percentage, right? But since we don't have any numbers, that's the best that we can do. And this basic idea about areas is what you're going to see the majority of the questions in the homework and on the test will be about. So are you actually going to ever have to calculate the areas? Oh, yes. But here's an example where the answer is no. So let's look at an example where you actually do have to calculate areas. All right. Oh, I'm sorry. We're going to do one more between that. All right. So this is one of the ones that are like tonight for homework. And one of the ones that you might even question, why is this a geometric probability question? So as we read this, it says every 10 minutes, a bus pulls up to a hotel and waits for 2 minutes while passengers get on and off. Then the bus leaves. If a person walks out of the hotel front door at a random time, what's the probability that the bus is there? When you're like, where's the geometry? Am I supposed to be drawing a bus and a building and some doors? No, they're asking you to take this whole scenario and see if you can somehow draw this out in terms of some geometry. And if it's dealing with time, that's the key here, right? Every 10 minutes, the bus pulls up, waits for 2 minutes. Then my suggestion is let's do a timeline. And a timeline is a number line. And so there's some geometry there. So the but here is, of course, what kind of the picture. So we're going to do a timeline. So let's see. The geometric shape we're going to use is a timeline. So there's my line. Notice I don't have a double arrow one because you can't go backwards in time. We're only going in one direction, so it's a ray. So let's see, at time 0, 0 will be the far left, and it says every 10 minutes a bus pulls up. So that means it repeats itself every single 10 minutes. So my timeline would end after 10 minutes and revert back to the 0. Well, let's see, I got to do what? 9 tick marks in between. Each one represents a minute. And it says every 10 minutes, so starting at 0, a bus pulls up and it waits for 2 minutes. So between 0 and 2, there's a physical bus right there. Some people might draw a bus. I just drew a yellow bar. And then the bus leaves, right? And then after 10 minutes, it repeats the process. So what's the probability that if you walk out at some random time that there's a bus standing right there? Well, it would be this scenario that's in front of you right here. The bus is there for 2 out of the 10 minutes. In other words, 2 over 10, right? If you're in the yellow, that's where the bus is, then you win the game. And then the entire things that could occur happens during that entire 10 minutes. So 2 out of 10 or 1/5, and that's 20%. 1 divided by 5, 0.2, so 20%. Okay, so here's your classic example of a geometric probability when it doesn't even seem like it's a geometric probability. All right, so you're going to see one like that tonight for homework. Here's another one. They're going to get relatively more challenging as we go on here. Oh, this is the classic one. I don't know why so many math books have archery targets or dart boards, but they like this one. They do geometric probability. Chances are you're going to see a dart board or an archery target. So it's a person who is just beginning archery lesson misses the target frequently. And that doesn't mean that that they miss the entire target. It just means they miss what they're aiming at. When a beginner hits the target, each spot is as likely to be hit as another. In other words, they're randomly hitting somewhere on the target itself. If a beginner shoots an arrow and he hits the target, what is the probability that the arrow hits a bullseye? Right? Now, hopefully you understand a bullseye is the center. And so it says if the beginner shoots and they hit the target, it's kind of randomly, the arrow goes anywhere it wants to go. So what's the probability that you hit a bullseye? The bullseye is the center. Well, think about that previous one with the weird looking regions. It's the same thing, except this time the regions are circles and we can actually calculate the areas of those. So what defines winning this game? Well, hitting a bullseye. Bullseye is the center. So what's the area of the red there? Well, it's a circle with a radius of, well, it's labeled with a radius of 1. So let's see, it's always this formula for probability. So let's see, the probability of the number of ways the event to occur, and that would be the area of the bullseye over the area of the entire target. And let's see, the red thing has a radius of 1, so pi r squared would be pi 1 squared. And the entire circle, it goes out to the blue. Well, the blue has a radius of 3. Can you see that label on the diagram? A little bit confusing. And then we're just going to reduce the fraction. Well, the pi's cancel, and 1 squared is 1, 3 squared is 9, so 1 out of 9, or 11%. So there's 11% probability if you actually hit the target at random that it will land inside of a bullseye. Okay. The last, we only got one more left. And the last one is very challenging. There is a homework problem like this, and I just want you might have to play this video again, or this portion of the video again, to understand the homework problem. All right. So if you ever played a game of chance at a fair, right? They always have those games where you're throwing something, you got to hit something. Here's a game. I don't know if you've ever seen this one at a fair. You're supposed to throw some sort of coin, and you're trying to just hit the red. There's lots of red out there, but your coin has to land precisely inside of the red. No overlapping, no touching. So that's the game. So it says at a carnival or a fair, you can toss a coin on a large table that has been divided into squares. That means multiple squares. And each square is 30 millimeters on a side. If a coin comes to rest without touching any line, you win. What are the chances of winning if you toss a dime? And it says a dime has a radius of 9 millimeters. Now, your book provides a picture of what this looks like. So it says you have a certain number of squares. And if you throw your coin on this table and it lands so that the red coin does not touch any black line, you win. If you touch a black line, you lose. And this seems like an impossible way to calculate unless I count up all the squares. And it turns out that, well, each single square has the same probability as any other square. So all we really need to do is just concentrate on one of the squares and figure out what's the probability that a coin lands inside of that one square. And that would be the same probability for any of the squares. So I'm going to expand that one square. And we're told that square is 30 by 30 millimeters by 30 millimeters. And then the coin is supposed to land somewhere. And if it lands without touching one of the black sides of the square, then you win. So clearly I've won the game here. Remember, the coin is a dime, and a dime has a radius of 9 or a diameter of 18. So there's one way of winning. And the question is, well, how many ways are there? Intuitively, you're probably saying, well, I need to calculate the area of that square, and that's not actually true. I don't really want the entire square because here's 4 possibilities. Each time the coin is not, I've tried to make it so the coin isn't exactly touching a black square or a black line right there. So notice I've got the center of those 4 coins drawn as well too. And the key to this is the realization that if I join the centers of those 4 coins like this, then that yellow section right there would represent the area that the center of your dime must be in. If the center of your dime is not on the corner of that yellow, but inside the yellow, in other words, the area of the yellow, well, then you won't touch the black lines that are on the outside of the square. So once again, I need to calculate the area of the yellow and compare it to the area of the entire square. Well, luckily for that, that's pretty simple. Each dime has a radius of 9. So if we think about, I don't know, if we think about this part right here, the blue part I'm drawing right here, well, right here is 9 and right here is 9, and the whole darn thing is 30. So 30 minus 9 minus 9, in other words, 30 minus 18 is 12. So that side of the square, and it is a square, is 12, and so is the other side. So the area of that yellow square is 12 times 12, 144. And the area of the larger square, 30 times 30, is 900. Reduce that fraction to a decimal, change it to a percent, and we get 16%. So you're probably wondering, well, why didn't I count up all the squares? Because once again, if we think about it, every single square is the same size. The only way I win is when I'm inside the yellow of each individual square. So every single square operates exactly the same way as every other square. So all I really need to do is calculate the probability for one of those squares, and I can extrapolate that for the entire game itself. Tonight for homework, you got one that's just like this, but instead of using a dime, I think they have you use a nickel or a quarter, and they tell you the dimensions, and you're going to solve it similarly as we did this one. All right, hopefully that one made sense. All right, so tonight for homework, you're going to have a bunch of questions on probability. They're going to give you some number lines and ask you to, pick a point at random. Do you land at this particular point? We did some examples like this. We did some examples of the bus one. So that's question number 2 right here. These are the classroom exercises. We did some ones with a archery target, right, or a dart or something like that. Same basic idea. And lastly, we did ones with the dime in the board. All right, so that should be it for tonight. I think you should be okay on doing the homework, but if not, as always, ask the question. I'd be happy to give you an answer. All right, have a wonderful day, and I'll see you next class.